Picture a constellation of NASA satellites, an orbiting sensor web designed to monitor the Earth like a networked sentinel, enabling us to learn vital information about one of nature's greatest threats: hurricanes. New research lets us see inside hurricanes like never before, to look under the hood and discover how the mighty engines of these storms work. Each summer and fall, the United States faces sieges from tempests whirling out of the tropics. Damage amounts to billions of dollars a year, from freshwater flooding, inundation by giant waves, and the force of 100-mile-per-hour-plus winds. Isabel was one of the most intensely monitored hurricanes ever, thanks to the current fleet of research satellites on orbit. NASA and NOAA collected thousands of images, and experts have been busy with the data. Isabel came to life in a continent half a world away, over far eastern Africa. At first, it was just a disturbance, tracked here in the clouds, beginning as a humble ripple in a steady flow of easterly tropical winds. Crossing the border between the fertile Sahel and the hot, parched Sahara, the cloud disturbance strengthened. The colors here show rain intensity, measured inside the clouds by the Tropical Rainfall Measuring Mission. Once out to sea, the warm waters of the Atlantic incubated the cloud disturbance. The cloud seedling rapidly transformed into Hurricane Isabel. As the core of Isabel warmed, the engine revved faster, and the winds whipped around the center at nearly 160 miles per hour. When it ultimately made landfall in the North Atlantic, Isabel had weakened markedly, but still remained a giant storm that devastated much of the mid-Atlantic. The ultimate energy source for hurricanes is the warmth of tropical oceans. The warm waters evaporate, and water vapor is the fuel that powers hurricane heat engines. But hurricanes feed back on the oceans that sustain them. The winds churn up the top layer of water, mixing up colder water from below. As this visualization shows, colder water trails in the wake of Hurricane Fabian. The waters have been chilled by 10 degrees Fahrenheit. But the high August sun warms the waters back up, just as Isabel crosses what's left of Fabian's wake. If we could peer under the hood of a hurricane heat engine, this is what we'd see. Satellites such as TRIM and QuickScat allow us for the first time to visualize the 3D anatomy of the storm. In a specially outfitted NASA DC-8, researchers probe the dynamics of a storm from the inside out. With periodic drops of precise instruments called dropsondes, vital data streams in that might otherwise be inaccessible, like temperature readings of the hurricane's eye. NASA's ER-2 also gathers hard-to-get data. Flying high above living, breathing hurricanes, elite pilots skirt the edge of the stratosphere to collect critical temperature and pressure data and other measurements. During a landmark mission called KMEX, these virtual satellites extended scientific vision on hurricanes immeasurably. Intense tropical rains fall from thunderclouds that ring the eye and create graceful spiral rain bands. A circular area occupies the tops of storms, warmed by giant rain clouds. Warm air, being less dense, weighs less, meaning the atmospheric pressure in the center of the storm drops. Into this low-pressure region, the air starts to swirl, turned counterclockwise by the Earth's spin, creating powerful winds that whip up enormous waves. Water vapor rising in updrafts through giant thunderclouds called hot towers condenses as the air cools. This condensation causes rain, and in the process releases latent heat into the atmosphere. Hot towers are the cylinders that do the work in the hurricane heat engine. Occasionally, during the early stages of a tropical storm, especially deep and vigorous hot towers called chimney clouds soar above all the other cloud tops. These amazing clouds are short-lived, but during their intense lives release a tremendous amount of latent heat inside the storm. If hot towers are the cylinders that power hurricane heat engines, chimney clouds are fuel-injected turbocharged versions. Rain is merely the byproduct of condensation in the atmosphere. It's what falls out of the heat engine after heat energy gets transferred upwards in clouds. The volume of rainwater produced by a hurricane during its lifetime is staggering, as much as 400 trillion tons in the case of Isabel. When this amount of water falls over land, the result can be catastrophic flooding and great loss of life. So, armed with all of this new knowledge about hurricanes, how are experts using it to save lives? These rich data sets not only enable us to better understand the physics of how hurricanes work, but provide input into sophisticated mathematical models that predict hurricane formation and behavior. NASA runs such a model on one of the world's fastest supercomputers, called Project Columbia. In this animation of the model's output, a single run captured the simultaneous formation of many hurricanes around the globe. Models like this, based on carefully collected data from NASA and NOAA satellites, deliver the most useful weather predictions. And they're improving every day. Better predictions means better hurricane protection for people around the world.